All righty, let's do a little review of the functions we've been looking at most recently. I'd like to first of all go with the numerical patterns. And first of all, if it's add, of course, that's a linear pattern. In fact, if it's add, but it's the second difference that's constant, we're quadratic. And if it's the third difference that's constant, that would be cubic. In other words, all your polynomials kind of fit this kind of add. It's just a matter of at what point does that second addition go constant. You then have the add multiply, which is very typical of exponential functions, and then the multiply, which is very typical of power functions. But as you start playing around with the words add and multiply, you realize there's one more combination we could look at, which is the multiply add pattern. What happens if the x's are going up in multiples or dividing, and meanwhile the y's are adding or subtracting? What kind of function would that be? Now some might realize, well, wait a minute, you're just taking add multiply and you're inversing it, you're flipping it around, so it would just be the inverse of the exponential. And that's kind of right, actually, but more on that in a moment. Let's kind of look at graphing patterns. So what I have are, lines and quadratics. Those are pretty easy to spot. It's telling the difference between powers and exponentials. So here's kind of a little review. Exponentials, remember, will always have that non-zero y-intercept. They could sweep upward, they could kind of sweep downward, but then they also have that horizontal asymptote. So those are the kind of the two giveaways that you're dealing with an exponential function. Now powers, on the other hand, there are a couple different varieties of power functions. When the power is greater than 1, like second power, third power, fourth power, you'll get this kind of curving action. But it always starts at the origin. And if your power is under 1, like maybe the half power or the 1/3 power, the curve will go in this direction, the so-called root functions, which are power functions. But again, things kind of start at the origin. Now, every once in a while, especially when you have kind of negative exponents, negative powers, you'll get this kind of a look where you really don't hit the origin, but you have kind of a vertical asymptote and then a horizontal asymptote. And so power functions have a couple different looks that you need to be aware of. So let's now move down to one that has kind of a similar look. And don't worry, I haven't forgotten about this. We'll kind of get to it in a second. But here's a pattern right here, and I've tried to graph the points of, let's see, 2, 3, which is right about here, 4, 5, 4, 5, 8, 7, 8, 7, and then 16, 9, 16, 9 right there, and I kind of drew the curve that goes through those points. And at first glance, you might be thinking, hey, wait a minute, that's one of these power functions right here. You can't fool me, this is a power function. Well, okay, if it was a power function, it should have a multiply pattern. And you go on the left side and you say, times 2, times 2, times 2. Just like I thought, it's a power function. It's got the multiple. Well, not so fast, my friends. We have to check the other side. 3 times 1 point something gives me 5. 5 times, I don't think I'm going up in multiples here. So how am I changing? Well, I'm adding on 2. I'm adding on 2. And I'm adding on 2. This is an example of this multiply add pattern that I was alluding to earlier. And maybe it is a power function. Let's think about this. If we were to kind of back up the pattern, let's see, dividing by 2. 2 divided by 2 would be 1. And 3 take away 2 would be 1. So 1, 1 would be right about here. I want to see, am I gonna hit the origin is what I want to find out. If I cut that in half again, that would be 0.5. And then if I subtracted 2 again, that would be -1. So I get 0.5, 0.5, -1. So it's not looking like I'm going to hit the origin. So it really is not a power function, either in terms of pattern or in terms of look. So what could it be? Well, it's going to be the fourth of the kind of the big 4 functions we're looking at in this unit. Okay, the multiply add is what we call a logarithmic function. A logarithmic pattern is the multiply add. Now it turns out logarithmic is the inverse of the exponential function. And you've been actually using that idea when you use logs to solve exponential equations. And we're going to talk a lot more about the sort of the algebra of logarithms next week. But for this week, we're just going to kind of focus on the pattern that exists in a logarithmic function. So in terms of the graph, okay, this is an example of a logarithmic graph. And it kind of has that curve of the power function, but it doesn't hit the origin. It kind of catches the x-axis. It actually has an x-intercept. And then it'll have this sort of asymptote, this vertical asymptote on the y-axis. So kind of the opposite effect of what we saw with the exponential, which is a y-intercept and a horizontal asymptote. Here, with logarithmic functions, we're going to have an x-intercept and we're going to have a vertical asymptote. So now let's talk about how do you find the actual equation for something that is logarithmic. Okay, well, of course, the first thing is to realize the pattern. This has a multiply add pattern, which makes it logarithmic. Okay, so what do logarithmic functions look like? Well, there are a variety of them, and so I'm going to give you one that we're going to kind of work with for now. We might change it a little bit later on. It's y equals a plus b log x. And the logarithm I'm using is the common logarithm, the logarithm with a base of 10. You could really use any base you want to with logarithms, but I think to keep things simple at the start, we'll stick with a logarithm base 10. It's probably the easiest one to get to on our calculator. And our task is to figure out what a and b are. So as we've done in the other problems we've worked on, we plug in some points. We have 2 things we don't know, which means we need to create 2 equations in order to solve the system. And so I'll just take the first pair of numbers and be 3 equals a plus b log 2. And I'll take the last pair. So 9 equals a plus b log 16. Which pairs you choose doesn't really matter. All you need to do is pick 2 points that you know are definitely on the graph, and you should be just fine. The algebra is going to work out just okay. So now the next step is to kind of work this out a little bit. Before you worry about, well, should I subtract these from one another? Should I divide them by one? And what should I do to kind of get rid of a variable? It's probably best off to, we're going to go ahead and convert these. We're going to find out the values of these numbers. So I'm going to go ahead and do the log of 2, and I get about 0.301. So that means my equation now is 3 equals a plus, and then this is 0.301 b. And then the second one, 9 equals a, and then I'm going to take log of 16. the log of 16 equals about 1.204. So plus 1.204 B. Now you folks who are really good with number patterns might recognize that this number is 4 times as much as this number here, and it turns out that is no accident. That happens, and it happens for a very, very good reason. But onward with the problem. Our task is to either eliminate the A or eliminate the B. So I'm just going to go ahead and do some subtraction. I'm going to kind of take this one away from this one. So I'm just going to rewrite it a little bit. I'm going to say 9 equals A plus 1.204 B, and below that I'll put a negative right here. So -3, negative A minus 0.301 B. And so I'm just going to do straightforward elimination as I've done in previous courses. 9 minus 3 is 6. The A's cancel. That was the intent. And then 1.204 minus 0.301 is about 0.903. So 0.903B. We'll do a little division. 6 divided by 0.903 gives me about 6.645. So 6.645 will be the B value. Okay, and to find out what A is, we can take this and plug it back into one of the two original equations. I guess I could probably use this one up at the top here of, let's say I'll go with the 3. So let's see, I'm not sure I have enough room there, so we'll try to fit it in, why not? 3 equals A plus, so if I put 6.645 right there and multiply by 301, so 6.645 times 0.301, it's right about 2. So I'm just going to kind of call it at 2.00. And so if I take away 2, I get 1 equals A. And so it looks like my equation is going to be, let's see, I'm just going to, y equals, and 1 plus 6.645 log x. Okay, and I believe that's going to be the equation, okay, of this graph. Now I could probably check it by doing regression on Desmos or regression on my calculator. I could plug in some of these points to see how well they fit the equation. I could even graph this and see if it kind of matches the graph that I have right here. So I'll go ahead and I'll do regression. Just always give you another example of regression. So again, I want to create a list, so edit. And so let me go up here and clear this down, and then over, up, clear, down. And so then I'll put in the numbers that I have in the table. So 2, enter 4, enter 8, enter 16. And then over here, 3, enter 5, enter 7, enter 9. And then let's see if it actually, or if it let me do regression. I didn't even think about this, but we'll go stat, okay, and slide over to calculate. And let's see if there's a logarithmic, there's a natural logarithm, there's an ln regression, there's an exponential, power, logistic, which is something different. Oh, unfortunately, so this one does not have log regression. It has a natural log regression, ln reg. So unfortunately, me choosing log, I'm out of luck as far as using regression. So then I'll go the next route and I'll say, well, let me just put in an equation and let's see how well this fits. 1 plus 6.645 log x. Instead of graphing it, I'm going to use the table feature. So I'm going to say second, make sure I enter that. Okay, and then I think I go second table. Okay, it'll give me a table of values, and I get some errors up here, which is okay, but the more important thing is, let's take a look at 2, I've got about 3, at 4, I got 5, at 8, I have 7, and at 16, I have about 9. So I'm pretty happy. This equation does seem to fit these points. So we have a nice nice equation. So that would be the logarithmic equation that would fit the given points. And if you're looking for a little extra challenge, you could use this equation to find out where the curve actually hits the x-axis. If you need a little challenge, see if you can find the x-intercept for this equation. If you also want another challenge, you could kind of ask, well, why am I getting these errors here? Why is it when I put in 0, -2, and -4, I get errors? And so you might want to think about why this leads you there. But I'll go ahead and stop for right now. Just wanted to give you the basics on the logarithmic function. Thanks for watching.